right, welcome to our last talk of the day. Now, before we get started, please remember there is a networking event downstairs at the Space Bar after this between 5 and 6 p.m. But before that happens, we're going to be looking at our last talk of the day by Louis Vainqueur, speaking about from transformers to true AI impact, building intelligent systems with MoE, multimodality and crowd of agents. Louis is head data scientist at Digitas, specializing in deep learning for NLP, causal AI, and network science. An early adopter of new technologies, he has applied his skills in startups, but also in strategic consulting and PE at Bain & Co. and finance at Market, now part of S&P. Louis holds degrees in applied mathematics, economics, and stats. He's a former adjunct teaching fellow at UCL and lecturer at EdHec Business School, as well as a member of a steering committee of UCL Venture PhD program. Please welcome Louis.
Thank you. Thank you very much. First, I'm going to say where I'm coming from. I'm from Digitas. We are the digital agency of the larger Publicis group. And I'm particularly part of the AI labs and practice, as well as heading the data science team. So the AI lab and practice is a unit that we've created about 2 years ago inside Digitas that allow us to continuously upskill our employees and at the same time build partnership to do R&D with some of our clients who want to do proof of concept or who want to deploy larger AI systems. So the agenda today, first I'm going to do a quick intro, but that intro I actually had to change this week because you probably have seen the OpenAI and Google I/O demos, and so that's what I'm going to talk about. Then we'll go through a few steps. We'll try to understand what is needed, but also what are the components that are allowing us to build intelligent systems. So first we need to understand language. Then with the models that already understand language a little bit, we need to scale them and add some memorization or some memory to them. Then we need to add vision. Then we need to add control. And I will finish with a few questions for you, actually, as well as my conclusion. So what happened this week? We've seen the Google Gemini update at Google I/O. We've seen what happened in OpenAI. They both have something in common, which is multimodality. What has impressed everyone is the fact that you could have models that can understand text, but they can also understand audio, video, they can understand drawings, they can understand people, really, because that's how we interact with the world. And so this is particularly relevant. It's actually more relevant than when I decided to do this talk, which was a couple of months ago. On the other side, you have other startup companies in that space, like Anthropic and Cohere, who are also releasing some tools that are not specifically on multimodality, but that are on methods to make those tools more intelligent. So we'll come back on this. So the first thing we need to talk about is how do those models understand language? And I won't get into all the gory details, but effectively, all of those models are models that are based on probabilities. So what they are trying to do is to infer or to predict from a set of words, let's say in that case 4 words, what will be the 5th one. But while they are doing this, they are finding a representation, a vector for each word that is being used in all those computations. And so this has a long history. A few years after I started deep learning and working in this field, we had a big moment, which was the Mikolov word-to-vec moment. I don't know if there is anyone in the room that still remembers this, but the first time I saw it, I was amazed, because that was the first time we could see a mathematical representation of some words that would make sense, and you could start building analogies with them. You could start getting some understanding of semantics, And so that allows us to move away from the previous keyword-based NLP, where you needed to have exactly the same word to be able to recognize it and make sense of it. Then came the second big moment in 2017 when the paper was published, the Transformer paper was published in 2017. And on this graph, I have three models. The T5 paper was not actually, the T5 model was not actually the model that was published then, but this is the model that is the closest to the original paper of 2017. And what you can notice is you have two variants of those models. You have the BERT model that we call an encoder model, because what it's trying to do is to take language and find a good representation of a sentence or a good representation of text. That's what it's trying to do. And on the right-hand side, you have the GPT model. Instead of just trying to find the best representation of text, it's trying to generate new text as you feed data through it. And so the original model had both sides, and now the model that effectively has, to some extent, won that competition is a GPT model that is largely adopted right now. You can still use BERT model for some specific use cases, but GPT now has taken over. And so both of those models are transformers models, and one thing that is underappreciated sometimes is that the actual transformer doesn't really see text, it sees indexes, it sees vectors. And here I've represented this path of transforming, starting with a question, transforming an input, so friends, Romans, countrymen, lend me your ears, transforming this input into a tokenized input, so an input where you split the element of that sentence into small bits that have an index in a vocabulary that you will use. And then later on, they will be transformed into a vector via a specific tokenizer and a specific model, and then propagated through the transformer model that I've just shown. And at the end, you will have another series of index that can be decoded into words. And that's what's happening in those GPT models. So here you have the main block of the original paper called Attention is All You Need. The main block is the self-attention. Attention hasn't been invented by this paper. It was invented in 2015, a couple of years earlier, but that was the first time that the self-attention mechanism was put together, scaled, and proved to work as effectively as it was. Prior to that, we were trying to play around with the recurrent neural network and inject attention into it. And at that time, it didn't work that well, but at the end, we can talk about this to see if they are coming back. So you have several steps. Here on the left-hand side, I'm showing the full cycle. So you have three matrices, Q, K, and V. What they are, effectively, is the input that you're pushing through the model. So you see that X here, that's just the input. We multiply that input by three different matrices that are, for example, from the start, initialized randomly. And so you will have the same message represented by three different matrices. And that's why we call self-attention, because the attention mechanism will do a dot product between the first two, and then divide it and scale it based on the dimension of the model you're using, and then multiply this, the outcome of this. It will take a softmax. So the softmax is effectively transforming this dot product into a distribution of probability. And then this is multiplied by a value matrix, which, as you remember, was also a representation of the input. So all of this to say that in practice, what's happening is that the model is progressively learning which part of a sentence is the most important for a particular word. So let's say that in your sentence you had 10 words. This process will create relationship between those words and the previous words that have been seen so that the model can know which word was the most influential and which word will be important to predict the next token. And that's, in a way, one reason why this is called the transformer, because at the beginning, you have a random vector, say, that represents a word, but that vector will be transformed and progressively transformed several times across the layers of the network. So now the small networks that we are using have 32 different layers of attention. And so at each layer, you will have such a transformation, and the representation of that word and that sentence will be propagated to the network. And here on the right-hand side, I'm showing how simple that can be in code. And if you see the blue part here is effectively doing most of the work. You have the softmax, you have a score. That score is coming from above. I don't have the full code here. Oh yes, you see the score. It's a matrix multiplication of the key. So that's the Q that we have here. The key by the transpose, or the transpose of the key by the query, and then scaled. And this code is actually part of the Llama 3 repo that you can access. So this is just to represent how simple the essential operation is, which I suspect is also part of why it's so powerful, because it can be scaled very efficiently. Okay. The second thing you can do to make those models more intelligent, once that you've allowed them to know what to look inside a sentence, what to pay attention to, and how to understand the sentence, you need to be able to scale this understanding, and you need to be able to improve that understanding with scale. And two papers were written on this who had a big influence. What people noticed is that there didn't seem to be a limit in terms of the number of layers of self-attention that you could put together. It seems that if you were improving or increasing the size of the network and increasing the data, and by data I mean the number of sentences that are passed through the model while you're training it, and increasing the number of parameters, you could keep on improving the quality of the model. And so the first paper was this one by OpenAI. One thing to notice, though, is that the authors of that papers, among the authors, you also have Dario Amodei, who is now the head of Anthropic, and you have many other people from there who are not at OpenAI, but actually moved to Anthropic. And effectively, those are the two best models, I suspect, today. So those ideas have continued to be applied. DeepMind had also the same type of analysis, except that they came up with slightly different formula of what should be the right combination of data, compute, and parameters in your model in order to train a very good model. And what you see on the right-hand side here is the application of this method. So historically, at the bottom here, you see the date. It goes from January 2018 to January 2021, I suspect. And you see that as those GPUs became more and more scalable and powerful, the size and the number of parameters of those models has continuously increased. And you will see that the BERT model, that was the very first one to be extremely popular, is now really a midget compared to models that already in 2021 we had. But something that is interesting is as the number of parameters of those models were being scaled, at the same time, they pretty much learned to do everything. And if you understand why, it's because when you're learning text, you're learning the next word. But for the next word to be the right next word, the model needs to understand a lot of implied relationship between the subject of that sentence, applied logic. He needs to understand grammar, otherwise you would make grammar mistakes. He needs to understand sentiment. He needs to be able to do translation. So effectively, the next word prediction turns out to be a very powerful method to learn a really large range of skills that the objective of the training model don't consider at all. And so one thing we can wonder, as you can see on the right-hand side there, you have a model with 1.6 trillion parameters, and I'll come back on this. And so the first question that came up when ChatGPT was published in 2022, November 2022, is what kind of model is this? Where is it coming from? And for a while, no one knew exactly, or I guess at least I didn't know, maybe you did. No one knew what it was representing until someone called George Hotz, that some of you may remember from his brief time at Twitter and Tesla. He basically went to an interview and said, oh, everyone knows what this model is. It's actually a mixture of experts. There are 8 experts, each one of them being 220 billion parameters, which is not, as you notice, very far from the best model, the bigger model that we see there, which was a switch transformer. And Sumit Chintala, who is originally was a lead on PyTorch, working for Facebook AI Research, he actually confirmed this on Twitter, and this became kind of the unproven hypothetical architecture of ChatGPT. So from that point on, we knew that the original ChatGPT model, at least, had more than a trillion parameters and was a mixture of expert model. So where are mixture of expert model coming from? I know that in our field we tend to think that everything happened yesterday, but actually that was created since 1991, and you will recognize that Geoffrey Hinton was part of this original paper. I think it's referred as the Jacobs and al. paper. And what a mixture of expert is a way to do conditional computation. And what that means is you don't pass all the data through all the parameters of the model. Some of the data is going to a specialized part of the network. And so that was the original idea. In that case, there was also a splitting of the training example between experts. So on that picture here, you see that we have three experts and one gating network. So the gating mechanism is effectively deciding how much data, where is the data going, and how much data is going through each branch, each type of expert. And then everything was average at the outcome of this model. It was also trained via supervised learning, not self-supervised learning, because self-supervised learning with text data is actually pretty recent. And it was originally built to do vowel discrimination. Then, in 2017, this paper from the Google team, again, you will see Geoffrey Hinton is there. He was on well, I was going to say he wasn't the main author, but I don't have the note there, so I won't say that. But it was published in 2017. I know that Noam Shazir was one of the person who really worked a lot on this with other colleagues at Google Brain. And what this model was doing, and keep in mind that it was published the same year as Attention is All You Need, so it was not a transformer at this point, but it picked back this idea of the mixture of expert, and back then I think it was using it between 2 layers of an RNN, actually an LSTM, which was the new kid on the block, well, not really new, but the very popular network architecture at this time. So again, the goal was to apply conditional computation, so effectively not pushing all the data through all the experts. And you can see that the mixture of expert layer was between those two layers of the LSTM. And that model was scaled up to 137 billion parameter. And the mixture of expert itself, so what you see in the blue part, was effectively a feed-forward network. A few years later, so in 2021, the switch transformer was published. And the switch transformer effectively took this idea of conditional computation and a mixture of experts, but used the transformer as opposed to an LSTM. And that was the paper that you saw on this computational graph going up to 1.6 trillion parameters. So there was an explosion in a number of parameters. And in that case, it was alternating between a feed-forward network and a mixture of expert network. As I mentioned at the beginning, those transformer models have the same block repeated 20, 30, 50 times, it depends on them. But in those separate blocks, they were alternating between MoE layer for the feed-forward network that you see there and traditional feed-forward network. And so you can see an example there with two different words. For the first word, it's going through the self-attention mechanism, so the QKV that I've showed before. There is a normalization. Then it's going to the router, and the router will decide out of those 4 potential experts, which one should I go through? And then it will go, in that case, to the second expert, and then continue its path to the next layer. And whereas the next word that is coming in the system is going to the feed-forward network 1, so the expert 1. And I think that's one of the essential bit of those models that are important to understand, is that they don't choose which sentence is going through a particular expert. They choose which token is going through that expert. At that time, there was also some experiment to try to push sentence by sentence, but it turned out that it didn't work very well. And people who look at that actually thought that this is not very dissimilar for a human brain, because when you're dealing with a sentence, there's not just one part of your brain that is being activated. The information can go basically pretty much everywhere. And that's how your brain will build some intelligent response. And so it made sense also that token by token, there is a different part of the network brain that is being activated. And so one hypothesis that they had at the time, not only the one who published this paper, but some others who worked with them as well, was that scaling the number of parameters while maintaining computation constant is beneficial. And what that means is, if you think about it, this is a 1.6 trillion parameters, but there is never one token that is going through more than 220 billion parameters, because most of the parameters are in, for a particular word, in the other experts that are not being used. And when you do that, effectively what you do is, with a network that has 1.6 trillion parameters, you only, at inference time, passing information through 220. So the first consequence is that it's faster, and the other consequence is that you have a much larger latent space to learn while you're doing training, while keeping the computation at a constant level. And obviously, that's what I was saying, sparsity accelerated inference. The other big learning of that paper was that distillation on those networks work very well. So they managed to reduce, on a particular task, the number of parameters by 99%, but keep 30% of the incremental gain in performance of that model. And we'll talk about that later because this might have a link with what we've seen with OpenAI and other players recently. And so this is almost, I would say, the human level MoE, the one we can actually play around with. So that was the Mixtral 8x7b million parameter model that the Mistral company open sourced in December last year. So here, like I mentioned, they are only using the GPT. This is from a very good blog post by Sebastian Rashka that it's worth reading. He has a very good newsletter. So you have the normal GPT model, but as you see, the multi-head attention is not touched, neither of those first two, but the feed-forward network is replaced by this MoE layer. And the way this is computed is that this MoE layer will select 2 of the 8 experts that he has, and the data will only go through, each particular token will only go through those 2 particular experts as opposed to go through the 8 experts. So even though this is a 8 times 7 billion parameters, it will never go through 56 billion parameters. No input will go through that, the full scale of parameters. And another consequence is that because you only replace the feed-forward layer, the actual size of the model is not 56 billion parameters. It's actually 47 because of the dimension of the feed-forward layer. And that's something that people tend to underappreciate. Even though the multi-head attention and self-attention is the most impressive part, let's say, of the network, most of the parameters are in a very simple MLP, which is a feed-forward network. And so that's why playing on this particular bit is particularly influential. And so if you look at the leaderboard, this is not from today, it changes every day, but if you look at the leaderboard in terms of Elo point of the best model, what you can see is the GPT model and this is pre-release of this week, but the GPT model from ChatGPT are rumored to be a mixture of experts. The people who were working on this at OpenAI before switching to Anthropic also have produced a model that performs very well. There were no information to my knowledge, and if you have heard about it, please come and let me know afterwards about whether this is an MoE model as well, but I suspect it is. And in terms of open source model, you have Llama 3, which is now number 6, a 70 billion parameter. But one thing we don't know, and that will be my question at the end, is what was that model trained on? We know it used 15 trillion tokens, but we don't know if there was some distillation of a larger model involved or not, because what we know now is there is a 400 billion parameters model being trained. Okay, the third part that we are going to see in terms of improving those models is how you add vision to them. So again, OpenAI to the rescue. The original model called CLIP was inspired by a lot of research and papers published by Stanford prior to the publication of this model. In particular, what Karpati had been doing with classification of image captioning. But when CLIP was released, they used an interesting training system that was a contrastive training. And what they were doing to train this model is effectively take a number of images with their proper captions, and then take this set of captions and images and feed them through a model by crossing the images and the caption. So only one caption would correspond effectively to the real model. So that's what you see on the diagonal. So this is when the caption and the image are a match. And theoretically, what they are learning there is learning a representation both for the image and the text that give you the highest score on the diagonal. So you train those two so that the model can learn to predict what is the right caption for a particular text. And so that's what they have done, and you can see it in code on the right-hand side. Effectively, they multiply the image features by the text features. And then you should get a higher score for the appropriate match and a lower score for the other ones. And this was basically generalized by other method, but this was the first very successful, at least, image text alignment. You have now more methods. So constructive learning is the one I just talked about. You have mask model. You have prefix language model as well, like the one on the right called SIM-VLM. You have multimodal fusion with cross-attention. I'll talk about this in a minute. But if we look at SIM-VLM, and this is the one with the prefix, what's happening is they are using an encoder-decoder model, and they append effectively the representation of the image before the representation of the text. And then this part, like we've seen at the very beginning, that's a bit like the original T5 model, where on the left-hand side you learn the representation, and on the right-hand side you generate. So they create one input, which is a concatenation of the image input and the text input, and then they pass this information to the decoder that will generate an answer. So you could use this for question answering, for example. This one is a cross attention. So this is called multimodal fusing, and this is exactly again using not only attention, but cross-attention. So when I showed you at the beginning QKV, so all three matrices were representing exactly the same input. When you have cross-attention, you could have the key or the query representing something different from the key, from the value. So let me say that again. You have QKV. Originally, it's self-attention because Q, K, and V are representing the same input. When you do cross-attention, one of them can represent something else. So one of them can represent, for example, a question, and the other one can represent another part of text or another part of the image. And in that case, the image is on the encoding side, so let's call this the query, and then the text will be on the decoder side. And that will be the key and the value. And that's what a model called Visual GPT was doing. So a concrete example of this approach, a concrete example of an MoE here was created by Avinash in a blog that he has published recently, actually last week or the week before. And he works for Databricks, so they build their own model, and he gave an example of how you would build your own MoE with existing part of the models that you could use. But this is, in that case, an MoE that is integrated inside a vision language model. So what you see on the left-hand side, you have an image that is an input. The image encoder will transform that image into a vector. Then there will be a matrix multiplication to project the dimension and align this image dimension with the text dimension, and all of this input will be passed through the mixture of expert language model, decoder language model. And then you will have some output. And if you look at it, it might sound complicated, but if you look at the code again, you see image embedding at the bottom here. There is an image embedding representation that will be created by, let's say, something like clip. Then there is a text embedding, and then both of them will be concatenated and then pass through the sparse mixture of expert blocks, which is effectively a transformer decoder. Then, this is a representation of the Liava model. So Liava is an open source model that you can use. You can have access to the code. You can completely transform. And it's showing something very similar. What is interesting on that graph is it's showing you what the model is doing differently at training time and at fine-tuning time. At pre-training time, they effectively froze the image encoder. They keep it constant, so that could be clip. And they only train the multimodal projector. So that's the layer that will align the representation of the image dimension with the representation of the text dimension. And so at training, you will only train this bit. And once this is trained, at fine-tuning, you can also change, unfrozen the text decoder, so effectively the transformer decoder side, so that the model can be more efficient. Okay, the last part, and I'll go quite fast there, is on how you can improve again those models with prompting, with memory, but also with orchestration. So one of the most significant and the most successful method you can use to improve those models is to use chain of thought. So what they call zero-shot chain of thought is basically just adding step by step. And you will notice if you've used those models a lot, in particular the open source one, that just adding this bit will generally give you slightly better outcome. But that's the naive chain of thought approach. You can have a manual chain of thought approach where not only you tell the model to think step by step and so on, but also where you give it a series of examples, let's say question and answer, the type of answer, but also you show it how should you think to solve that particular problem. And so you give really the chain of thought of your example so that the model can learn how to solve those problems later on with new example. And then, so that's the one you see on the right-hand side. That the second one, that's the chain of thought, traditional chain of thought prompting. Then you have something called chain of thought with self-consistency. And this takes into account the fact that those models are effectively stochastic model. And so you could generate several answers with the same model, for example, by just improving or changing a parameter like temperature, which impact the stochasticity of the probabilities that are coming out of the model. So you could generate several outputs and then just look at the majority vote for your particular question and then take this as the best answer. And what that means really, because we all know that a problem with those models is hallucination, is that the model will tend to give you the right answer more often than it will tend to hallucinate. So that's your hypothesis there. And then you have something called tree of thought, and that's a more involved and program-based system to let the model decide when it's going to hit a dead end, and so potentially retract from its current path of thinking in order to get to a better answer. Another thing you might want to do is to add controllability to your system. So again, the output is stochastic. You have, if you just train to predict the next word. The model might not be aligned with what you want it to do. It might not be set up to answer proper instruction. So that's where you use supervised fine-tuning, but also where you use reinforcement learning with human feedback, or direct preference optimization, which allows a model to learn how you want your response to be, how you want him to follow instructions, and so on. So on that side, the model will effectively learn a reward model that will allow it to score quality of answers and then to search the latent space to give you the best possible answer. Another approach is what Anthropic is doing with constitutional AI and safety research. Unfortunately, there are some trouble in that space, but that would need another conference altogether. So we won't talk about this too much. And there is also mechanistic interpretability, which is the ability to get within the network to analyze the input and output of the network to understand effectively what the model is thinking, quote unquote. A framework to make those models more intelligent also is similar to what we've seen previously, but that's a React agent framework. And what the React agent framework is trying to do is give the model effectively something to think about and give it instruction in terms of thought. So what it is doing is it's looping thinking, planning, and observation, then more planning, then more observation, and so on. So it's trying to follow a reasoning trace that you will try to inject into it with your prompt or with the way you set up your system in order to give you the most intelligent answers. And what you see is, just like self-consistency, you reach better level of accuracy when you do that. Yet another way to improve model is to look at the same model with unique output or multiple output. And what you have on this graph is from Andrew Yang. What they have done is looking at a coding benchmark and benchmarking GPT-3 versus GPT-4. And you see that if you only have a single answer, a zero-shot answer from GPT-4, you're reaching 70% versus only 48% for GPT-3. But if you add agentic framework around it, so effectively multiply the LLM by using an agent framework or even use tools to get to that answer, you can reach almost 100%. I think that's 95% or so by using those frameworks. So there are a lot of practical implication of this. What that means is you can get to a more intelligent system even though you're using some models that are partially dumb, just by putting them into the right framework and using agent and prompting in the appropriate way, which has a cost implication. Obviously, like I mentioned in the React system, you have effectively a thinking process and an acting process. And you could decide that your acting process is effectively a dumb process, so it could go to even an open source model that is free, while your thinking process is high value, and for that you might want to use GPT-4 Turbo, for example. And so you could combine those two approaches in order to optimize quality at a reduced price. This is yet another paper that has analyzed this approach, and you can see there how with a Llama 2, not even Llama 3, you can approach GPT-4 performance, even though the model is much, much dumber. And so this is my conclusion, really. My conclusions are really questions. So first, what is the architecture of Llama 3 400B? Obviously, I would like to know what's going on the GPT Omni side as well. But one of the questions I'm asking myself is whether those models, for example, we've seen that GPT-4 Omni is much faster than GPT-4 Turbo, which makes me think that it's much smaller. And if you remember the lessons that we got from the switch transformer, you can actually keep the performance of a much bigger model by distilling a mixture of expert model into a smaller model. So I'm wondering whether this is what's happening with Omni, GPT-4 Omni, which would explain both why it's much cheaper and much faster. And the other thing is whether there will be a link between controllability and scale. And this, I don't have the answer, but if you do have it, please let me know. Thank you.
That's some really great food for thought and some good reflecting questions for us at the end. What I will say is if you do have questions, I know Louis is going to be downstairs for the network event after. And just to say to everybody, thank you again for joining us today at the Data Science Festival. A huge, huge thank you to the speakers, to the volunteers, the sponsors, and the AV team who have made this day what it is. So please give them a huge round of applause. And if you had fun today, the ballot is now open for Oktoberfest in 2024, which will be happening back here at this location on October 19th later this year. So, to finish off today, please join us downstairs for networking and drinks. Have a great Saturday evening.